Yeah, yeah, I'm doing that one.
Okay, sir. So, like, by when will
Maybe
we?
tomorrow evening I'll call. Okay.
Okay, sir. And also, sir, since we are on campus only,
Yeah.
can we meet at a regular times in some
Yeah.
classroom?
Actually, what happened now? Now see again. Now I have a. We are having an engagement from 5 to 9 today. Research scholar meeting is going on in the we first. Okay, but
Exactly,
somehow
sir.
somehow I just took some time and came here. Okay, so that I can engage you guys. Okay, but I feel it is also you are right, correct. We will meet on time only and at the right place. Okay,
Exactly, sir.
the
Yes.
things will be getting accelerated in that way. Okay.
Yes, sir.
Okay. So tomorrow we have class at 10 o'clock.
Yes, sir.
So which is the room number? Do you remember?
Yes, sir. I'll just let you know. It is
One two
one.
three two.
Yes, sir. 1232.
1232. Okay. So we will meet there only. I'll come with my laptop. Okay. We will meet there only. 10 o'clock tomorrow.
Yes, sir. Yes, sir.
Okay. Fine. Thank you. Annual it is an annual event for all the PhD scholars. Okay, where they need to showcase their work. So it is today, 5 o'clock onwards. It has started already. All the faculties are there in VFast lawn. Okay. But I told no, I can't be there for a long time. I have to engage the classes. So again, I will rush there at 7 o'clock. Fine. So
Yes, sir.
anyway,
Yes.
yeah, these things will be keep. Oh no, why I'm doing what I'm doing? Okay, recording has started.
Yes.
Yeah. See, let me know if you are able to see the screen.
Yes.
You are able to see. Fine.
Yes, sir.
So when we started when we started composite material, these things are some of the very basic things that we looked at. That composite materials are basically macroscopic mixture, in the sense that if you mix fibers and your matrix material, okay, you will be able to see that where are my fibers and where are my matrix. Means the mixing process is not a complete homogeneous one. That means even after the mixing, you will get to know that which is the location of fiber and this thing. So and that cause actually a lot of trouble in the modeling part. Okay. Why? Because when you try to model composite material for an structural analysis, definitely you require to know the stress distribution inside the structure, strain distribution inside the structure. But when you change your location from one point to another point in the material, sometime you are landing on the fiber, sometime you are landing on the matrix, or sometime you are landing on the fiber matrix interface. So in this way, the mathematics becomes very tedious, and it requires a lot of assumptions to do. Okay, and this is the reason that a multi-scale analysis is always proposed for the composite material. What does it tell? What does it mean? It tells you that based on the scale of analysis, means the scale in the sense the you can say scale, you can compare here as the visibility. Okay, how much quantity of the composite material you are going to analyze at once, that decide the scale of analysis. If you are just analyzing only fiber and matrix, okay, a small section fiber and matrix, okay, with the interface, okay, then that will come into the micromechanics of the composite material. So it has its own mathematical formulation to care of that, like we have seen that if you have fiber and matrix, and then you will come to know about what is the fiber volume fraction for fiber and matrix. And if you know this thing, and if you know the Young's modulus of fiber and matrix, then you can get the value of Young's modulus in one direction and two direction of the composite material uh, for this using the macromechanics approach. And there are we looked at many methods based on solid mechanics, then semi empirical methods, then using the theory of elasticity methods. Okay, so that those things we were doing just to get the value of my mechanical property of this representative volume element that is called as RVE, and we are going to get the Young's modulus of this one, stiffness in one and two direction. And it is already clear to you that the composite material will have different stiffness in different directions. Okay, so we started with a very simplified case that we took just a two-dimensional structure of a composite material, where there was a one fiber and matrix was there, and we were just looking into what is modulus in E1 direction, what is modulus in E2 direction. But the life is not that much simple, that where you are having already always two-dimensional structure. You are in reality you are going to have a three-dimensional structure. That means now your life is bit tough. Here you have to get the value of E1 also, you know, you should know E2 also, and you should know E3 also. Similar fashion, G1, G1C, G2C, G31, lot of things are there, you should know. So as we move, as we increase the complexity of the problem, we are going to have more and more mechanical constants are coming into play. Okay, so this we have seen in the micromechanics part now. But once I get the value of E1 and E2, okay, then we can directly use these things in our analysis. So what does it mean? It tells you that you take the smaller piece of a composite material, you try to get the value of its volume fraction and get the value of your E1 and E2. And this and E1 and E2 will represent the E1 and E2 of a lamina. Lamina in what is called as lamina is a thin sheet of composite material which has only one layer. One layer means there will be one layer of fiber, unidirectional fibers will be there, and there will be matrix on this one. So how it will look like? It will look like something like this. You see, this is the lamina. Okay, it has matrix and fibers are there. Okay, but it will be make you will make it as a one sheet, thin sheet. Okay, and when you paste a number of lamina together, you see, if you are pasting different laminas together with where the fibers are oriented in a different angles, like see, these fibers are going in this direction. Okay, and these fibers are going in this direction. So this means this is stacking, this is called as stacking sequence. Okay, and this stacking sequence is, if you assume that this is 0 degree angle, then this is 90 degree angle. So our stacking sequence is like that: 0, 90 degree, then 0 degree, then 90 degree, like this. So this is the term, how we write the stacking sequence. And so up to the lamina means when we are having a fiber matrix and I know the volume fraction, I will get the value of E1, E2, and yeah, E3, G1C, G23, like all the things using the macromechanics approach. But once I know these things, then I can directly use them in the laminate. So when I'll be analyzing a composite material in the form of laminate or in the actual structure, I will just use these values. Okay, no one will ask me what is the volume, fiber volume fraction here of your fiber and matrix, like these things. No, or the lot of coupling terms were there that we have seen in the macromechanics, that the degree of coupling, some other word was there for that one. So those things no one will ask me. Now everyone will ask me what is E1, E2, and E3. So what we are doing actually here, see, lamina is a thin layer of composite material that is generally of a thickness of order this much. Very less thickness will be there. Okay, few fibers will be there, and matrix will be there. And what will happen then? When we put different laminas together, we will get a laminate. Okay, this is called as laminate. Okay, you see a finite element image here. You see here different laminas are there. One layer, two layer, three layer, fourth layer, five layers of laminas are there. Okay, five layers are there. And when when we put all the laminas together, we made a laminate. Okay, now this laminate, we are, because composite material is known for its strength also. A lamina itself will not be able to provide you that much strength. Okay, and so we have to club lot of laminas together. Okay, and we get the value of laminate. Now, the one question may come to your mind that, sir, why we are doing like this? We can make a laminate directly. We can make a thick laminate like this one. Instead of making something like that, we can make a thick laminate of like this one and do the analysis. Any type of structure we can make up only. But what is happening here, composite material, it will have different property in different directions. Okay, now you just assume that you are making a maybe I'm making a turbine blade, okay, of a composite material. Okay, and I'm putting the composite materials are put in a such a way that the stacking sequence is 0 and 90. Okay, 0 and 90. That means first layer is that there are two layers. Okay, like this one, two layers are there. In the first layer the fibers are going like this one. Okay, and in the other one the fibers are coming out of the board like this one, like this one. Okay, so what happens if if there is a situation that if you find that the air drag or any force which acts on the this turbine blade in this direction, at that time these fibers which are oriented at 90-degree, they will come to rescue the uh, your turbine blade. Okay, but nature is not very certain. There may be chances that after some days the wind starts blowing in this direction. Okay, at that time what will happen, these fibers which are oriented at 90-degree, they will come to for the rescue, or they will bear the load, and that time these fibers which are aligned in the zero direction, they will not have much role to play. So based on the uncertainty in the design, in the loading condition, we are doing these iterations. Okay, we go to the actual site and see what is the wind direction. Maybe sometime there may be that a wind is blowing at the 45-degree. Okay, so what we do, we will put one more layer on this one where the fibers are oriented at 45 degrees, so that what happens, when I was telling you about this thing, composite material, if I just take a lamina of a composite material, okay, where fibers are oriented like this, and I told you that in this situation the composite material will be able to sustain maximum weight when the load is applied along the fiber direction, because fiber bear more weight. Fibers are stronger than the matrix material, so the fiber has to align along the loading direction, then it can bear more weight. Okay, so in this way you see here, like when the fiber is in the zero direction, then it will be able to counter the weight, the load which is coming on this one in this direction. If air drag or anything is coming on the 45-degree, these fibers will be activated. So it is like something like different switches are there in the structure. Based on the loads are applied, different switches are getting triggered each time. Okay, and each time your surface, your structure is getting each time your structure is saved. Okay, so these iterations, okay, these iterations are this combination is actually decided by the engineers, okay, based on the loading condition. Just wait. Just wait for one. Give me 1 minute. What has happened to my system? Hello, are you able to hear me?
Yes, sir.
Something happened to my system actually. It is stuck somewhere. Just Okay, now it's fine. I'm audible to you. Hello.
Yes, sir. Yes, sir.
Is the thing fine? Okay. So that's what I'm telling you. Instead of uh, designing or making a very thick composite material, we go for stacking. And you can also ask that we here also we can do, sir, that we will put one layer of fibers like this, okay, then other layer of fiber like this. You can do, but the design will be very difficult because when you are starts manufacturing a composite material or a laminate, the glue or the epoxy material or the matrix material will be in this liquid form, okay. And in the liquid form, settling this to setting up of these fibers into a particular orientation is possible only in one orientation. You will be able to do it perfectly. Otherwise, if you put one layer like this, the other layer going like this, other layer 5 to 5 days, there it will not settle very well, okay. You will not get a proper uniformity. So that is the reason what we do. We make one layer completely with in one direction, other layer in other direction, other layer in other direction, and then we put glue in between these two layers, okay. And then we make our composite structures like this one, okay. So this is the way that things are done. So in this way we can say that the lamina means a single layer of fiber and matrix is the building block of a laminate, okay. And when the mathematical formulation for laminate is again different. That's what I'm telling you. It's a very very the composite material. This is called as a multi-scale modeling, okay, of the composite material. Means we need to see at what scale we are going to analyze the thing. So so when we see only the fiber matrix, it is called micromechanics. When we see fiber matrix on only one layer of this one, okay, that will come into either this is sometimes it's called as meso label also, okay. And when we take different stackings of these fibers and matrix, okay, then that will come into micromechanics. And then other thing is the structural mechanics, where we take the entire structure made up of the composite materials and do the analysis, okay. So this is the thing I wanted to tell you. Now, coming to the thing that when we want to know the strength of my laminate, okay, from where I am going to make my actual structure like this one. If I want to make this pressure vessel, okay, I need to know that what are the different laminates we are using here, okay. But when I want to qualify this, when I this structure is we want to qualify it for some stress level and strain level, that these allowable stresses and allowable strengths, I should know the strength of my laminate from where I weld this one, okay. And to know the strength of the laminate, I should know the strength of my lamina from where these laminates were made, okay. And this will again and the strength of my lamina will again be determined by the fiber volume fraction and all the things. So the things are very much related. Means the output of my micromechanics, so it is understood like this one. The output of my micromechanics, for like what I am going to get E1 and E2 and all that things, will be an input for mesomechanics, okay.
So
And
just to clarify,
yeah,
in the typical finite element
yeah,
software,
yeah.
the solver will start by solving equations for the micro scale, and then it will use the results for that for the
No,
macro
no, no,
scale,
no,
and like
no.
that.
Actually, in the typical softwares, they will directly ask you these values.
Oh, okay.
E1 in E2. Okay. See, few of my students are working in this level also. Okay, mesomechanics. Okay, maybe if you allow me, as we are here to learn the things. Okay, I'll just go to my maybe I'll, maybe as you ask me, so it is better that I should show you something which is really going to work for you. Okay, you see some papers I'm showing you. Okay, not this one. It, See, are you able to see?
Yeah, yes, sir.
See, this is actual work. This is experimental work. People have made a composite material in the lab using fiber and matrix. Are you able to see?
Yeah, yes, sir.
Okay, and somehow they are trying to mimic that one in this structure. You see, fibers
Right,
and matrix are there. Okay, and here they are applying the, because here I can calculate the fiber volume fraction easily because I know the geometry of my fiber and I know the volume of this cube. Okay, so from there I will know the volume fraction of fiber and matrix. Then I will be finding the what is the different E1 and E2 value of this one.
right.
Okay, experimentally this is how means the things work in this one. Maybe this one like yeah, this is exactly the work one of my student is doing here. Okay, you see here the structure is like this one. Matrix is there, fiber is there, and in between there is a coating on the fiber. Sometimes we put protective coating on the fiber also. Okay,
Right.
so we have to model that one also. You see here, this is a one of the representative volume, but when we see like you see here.
So finite element method can be applied even to the representative volume
Yeah,
element.
that's what I'm telling you.
Okay.
Based on the scale at which you want to analyze. Okay, like if someone gives you a work that he wants you to get the value, particular value of E1 and E2 value. Okay, then what you will go? You will analyze the composite material at this level, micromechanics level.
Right. Okay,
Okay,
sir.
micromechanics and the output of, that's what I'm telling you. The things are very much interrelated with each other. And this is not happening in metals. Why it is not happening in metals? Because if even if you take a small piece of metal or a intermediate piece of metal or a very big slab of metal kept somewhere, okay, everywhere the your Young's modulus and Poisson ratio for all the things will be same.
Right, right, sir.
Okay, but as we are in the composite material, you see different things are going to happen here. So the output of macromechanics is actually used to as an analysis for mesomechanics. Okay, and then that will be used for the macromechanics like this one. So based on the thing, so but in the macromechanics level, you need not to worry about what was the fiber volume fraction, what was the shape of the fiber used. Okay, how is the bonding between the fiber and the matrix? Nothing. They just want the average values of E1 and E2. Okay, and they want to do the analysis.
Okay, sir.
Okay, this is how the things. Okay. So now this is this was I was telling that the strength of your laminate will directly be governed by the strength of the lamina, and when the strength of the lamina comes in, the strength of the fiber matrix, lot of things are there. So we need to see at which level we are going to analyze that sequence. And this I told you that if you apply a load, just you see, this is a cross section of the wing of an aeroplane. Mostly the wing of an aeroplanes are like this one, made in an aerodynamic manner. Okay, so it's a cross section. So if you apply a load comes on this one, if a bird strikes on this one or something happens on the wing of the aeroplane, and I want to analyze that how much deformation it has made in finite element, I should know that at what was the location where bird has struck, whether it has struck it made a strike on the fiber part or matrix part or the interface part. Okay, this is the thing that is creating all the issues here. Okay, so what will happen in the micromechanics approach when we are analyzing the structures as a whole composite material, we take the average value of E1 and E2, whatever the value the micromechanics has sent to me, I will use that one to find the average value. This is called as a process is called as homogenization. What it tells me that though the composite materials are anisotropic and non-homogeneous, okay, but for the modeling purpose we just assume that okay, now for this case I will not care that whether it was like the collision at the fiber or matrix, but just I need the value of E1, E2 and all the mechanical properties of composite material. I should be able to do the analysis. It is not also correct always. Okay, it is not also correct, but we can't because in the next slides when I'll start showing you the mathematics of this macro mechanics, then you will find that how the life was tough when people didn't make proper assumption. So with proper assumptions and simplification, only the composite material analysis is somewhat possible. Now you see that this is just a um, mm, introduction, okay? That what is the you know uh, like okay, maybe I will not go much into this one.
So this was
Now,
there in advanced Excel.
yeah, advanced Nextol. Now, these things was not there in advanced Nextol. What it tells you actually, you see here, there is term called as fully anisotropic material. Fully anisotropic material. It's a very means it's not there in other books also, but somehow I managed to get it. You see here, if you take a small cube, okay, a representative volume, a cube, a three-dimensional structure, okay, then there definitely you will have stresses like this one. Okay, now what does it tell you? It tells you these are the normal stresses acting on the cube. Normal stresses which are pulling the cube up like this one. Sigma 33, sigma 22, sigma 11. Okay, and these are the shear stress system. Sigma tau 1 2, tau 2 1, tau 1 3, tau 3 1, tau 2 3. These are the shear stresses. So how many stress term you can get at a point? Three normal stresses and six shear stresses. So altogether nine stress components you have to get at a point. You need nine stress components to define stress state at a point. Okay. Now, in the similar fashion, you will have nine strain components also at a point because all the stresses will have a corresponding strain. This stress will have a corresponding strain 2, 3. This stress will have a corresponding strain epsilon 2, 2, like this one. Okay. So now what you are getting, you have nine stresses and nine strain components. So in order to put them together, a perfect relationship has to be created between the nine stresses and nine strain components together. Why I'm carrying with the nine word? Why? Because here still I am assuming that tau 1 2 and tau 2 1 are different. Okay, but tau 1 2 2 and tau 2 1 is different. Okay, they are not equal. So if I assume that these things are not equal, okay, I will get a situation like this one where I'll have nine stress components and nine strain components, and they will be in relationship with this. It is a material property. Okay, like this one, and this is called Sijk is called as the generalized stiffness tensor. Okay, so you see here all together, and this one Sijkl will have 981 elastic constant. That is called as for a fully anisotropic material. Fully anisotropic material means in the isotropic material which don't have any symmetry, any type of material symmetry. In absence of any type of material symmetry, we should have 9081 material constant. Okay, however, the thing I started qualifying now means simplifying now, that principle of equilibrium if you take on each side of this one, then we find that these things are equal. Tau 1 to tau 2 1, and these shear components are equal. That means instead of 9 1 2 3 4 5 6, okay, instead of my 6 strain, what is called as shear components, I will have three only, three independent. Okay, so now you see here what is this three. You see here first, if I have nine stresses component and related with nine strain component, you will have a situation like this one. A very big stiffness matrix will be there relating with each other. Okay, and when I put in the terms of strain on the left hand side and stress on the right hand side, I will have a situation like this one. So if I have stress here and strain here, then this is called as stiffness matrix. This entire matrix is called as the stiffness matrix. Okay, and if I have strain on this side and stress on this side, then this is called as the entire matrix is called as compliance matrix. These are just two reverse things. Okay, these are they are very much related with each other. Okay. Now what happened? But this I will. It is not there. The proof is not there in proof. I'm not going to show you. It is told that the EIJKL and EJIKL are same. Means these two terms you see here. This one and 2 3. Where is 2 3 1 1 2 3? Yeah, this is my diagonal term. Okay. Now, what is happening actually here in this one, in this case, when I'm taking a bigger stiffness matrix, like this is my diagonal term. Okay. Yeah, actually this word has gone to that one. This line should come there only. Okay.
Yeah, sir, I understand.
Yeah. Got now. So the cross diagonal terms will be same. Okay, maybe I'll just okay. So from 81 material constant, I will land into 54 material constant, and then there again, if there is symmetry, that's what you see here. I am writing here fully anisotropic material which lacks symmetry.
So, is there any example of a fully anisotropic?
All the materials which is available in nature is fully anisotropic material.
Okay.
Okay, but we try to simplify the thing. We try to find that there may be chances that if we find some symmetry in the structure, okay, okay, then we tell that the for symmetrical anisotropic material, our material constant like sigma ij is equal to sigma ji, and these things are also equal. So you see here what is the thing that we can assume that the strain component, these terms tau 1 3. Before sharing the slides, I will just modify a few points here. This is not very clear now. Okay,
No problem, sir.
I will do this one. These two things are equal. So now you see here, finally we start, in all the books, the things will start from here only. 36. Okay, they will just tell you that for the definition of stress at a point, they will put a cube, three-dimensional cube. Okay, and they will tell that you have sigma 1, sigma 2, and sigma 3, and you have stress component sigma tau 1 2 tau 3 1, like this one. They will start from here only. No one will, rarely any book will start with 81 material constant, but the truth is that the material constant will be always 81 for a fully anisotropic material. Okay, but for a symmetrical isotropic material which has planes of symmetry present in that one, I will start with the 36 material constant. So my stresses will be sigma 1 1, sigma 2 2, sigma 2 3, 3 normal stress and 3 shear stress. Okay, so from here only, in fact for our course also we should start from here only, but just for giving a to give you a bit more detailed explanation and detailed overview of composite material, I just took these two extra slides which are just before this one. So just you for youth case, you just assume that for a point in the stress of isotropic material, you have three normal stresses and three shear stresses connected together with your three normal strain and three shear strain using this stiffness matrix given by this one, which has 6 by 6. It is 6 by 6 stiffness matrix. It's a fully populated one. You see here. You have all the elements in the diagonal. Okay. This is called as fully anisotropic material. Okay. No, this should be not fully. This is a symmetrical anisotropic material. But I will tell you one thing. So sometime what I told you that instead of writing this much big expressions, okay, S111, S1122, like this, we write in a simplified fashion like this one. The stiffness matrix elements in the diagonals are written like this one, and the cross diagonal terms are like S12, S123, like this one. Okay, so this is called as contacted notation for an isotropic material. It is right. I need to correct a lot of things in this slide before sharing. Okay, I need to correct.
Okay, sir.
Okay, okay, I will do that one. So if I write in terms of stress here and strain here for a symmetrical isotropic material, anisotropic material, I will do like this one. Stress here, then I will write stiffness matrix, strain here, strain matrix. Okay. Now you see here what happens actually. These groups are not there. Okay. Now and equality of cross shear and something using that thing. It is told that though we should have 36 material constant here to correctly define the stress, make a relationship between stress and strain. I due to the equality of cross shear. Okay, these cross diagonal terms are equal, like you see here. S12 will be equal to S21. S13 will be equal to S31. Okay, cross diagonal term. Okay, that means the 36 material constant will actually reduce to 21 material constant. You see here how much we have started 81 to 54, 54 to 36, 36 to 21 material constant. And in fact, then we will go for 9, then it will come for 5, and it will come for finally 2. And this is the most simplest one, that is called isotropic case. And this is called as transversely isotropic. This is called as orthotropic material. Okay, this is an general anisotropic material, and this is your fully anisotropic. So lot of things are there. You see that based on the material constantly, our life means how the things were very complex here. Okay, so we need to deal with now 21 material or 21 material constant for an isotropic material. Okay, for making or to define all the things. Correct. Now, what is there actually? So instead of writing the when we came to know that there lies symmetry, there exists symmetry due to the symmetry in the stiffness matrix. Okay, instead of writing 36 material constant, we can write 21. So what we do when we write in the simplified form, we write like this on the stiffness matrix. We write like this one. Okay, and this symmetry means that these things, the whole this one is again going to come here. Okay, and this is how. So this is called as generalized Hooke's law in Weigert notation for an isotropic material like this one. And so these things are yeah, okay. Now, what is actually the difference in the why anisotropy is going to create a lot of issue for you? This is a very good slide for you. You see here, you have stresses on one side and strain on one side. Are you able to see?
Yes, sir.
So if I have an isotropic case, very small means very simplified isotropic material like your steel or aluminum, what is there? You have stress directly related with your strain through Young's modulus. Okay, and actually this Young's modulus is the thing stiffness. Okay, and when this we are writing in one dimension. Okay, and when we are writing the three dimension, the stress, instead of one stress it becomes six component strain. One strain becomes six strain, and stiffness, this Young's modulus becomes a stiffness matrix like this one. Now you come here, you just be with me for some time. You know matrix multiplication very well. If I want to ask, if you want to get the value of sigma 1 1, if you know the strain and if you know the this material properties, I told you that the strain is the most basic thing. When you take you put strain gauges on the structure, you apply load, the strain gauges will measure strain, and if you know the stiffness of your material, then you multiply with the stiffness terms, you will get the stresses. So if I want to get the value of sigma 1 1, I will do the matrix multiplication of these whole terms with this thing. Okay, so what I'm going to do, I'm doing sigma 1 1 is a normal stress, and when I'm doing the multiplication, I'm getting a multiplication of normal strain components with this thing S11 S12 like this one. Then I'm getting a shear strain components are coming here. Now what is it is telling you? It is telling you that the normal stress, if you so if you are getting a normal stress will have strain contribution from strain normal strain components. You see, normal strain components are there, and in spite of that, you have contribution from shear strain components also. That means shear strain components will also contribute into the development of normal strain stress. In the similar fashion, if I want to get the value tau 13 or tau 12, if I do the matrix multiplication, I will get that in reality it look to me that the normal strain should produce normal stress, shear strain should produce stress. But here the things are happening in a different way. You see here, shear strain is getting accumulated due to normal.
I understand, sir. Basically, if you
Okay,
apply
so
shear stress, that
yeah,
is
so
normal
this is
strain also.
this is
And
called as extension shear coupling. Okay, if you apply shear, it will give you normal stress. If you apply shear stress, it will give you normal stress. Means the things are coupled here, and that is the reason you see here. Just if you have a composite material like this one, which was a square or a rectangle initially, and if you are applying a normal load, it is showing you the deformation in the shear in the this one shear form also. Shear deformation is also coming here. Similar fashion, if you have if you apply just shear load on the composite material, okay, anisotropic composite material, it will show you the normal deformation also. Not only the deformation in this direction, but some deformation. This is called as the extension shear coupling. Means the normal deformation will be contributed by the shear strain also. Okay, and your shear deformation or shear stresses will be contributed by the normal strain also. So this is the thing actually which makes the life very complex in the composite material analysis, where you have extension shear coupling, and such thing is not observed in isotropic material. Okay, normal stress will always produce normal strain, shear stress will always produce shear strain. So this is the thing that you should know, that what is extension shear coupling. Okay, so up to here we will just leave it. Tomorrow onwards we will start monoclinic, orthotropic material, isotropic, all the things we will see. Okay, is that fine?
okay, sir. Yeah,
Okay, so we will meet tomorrow at 10 o'clock only at the class, and we will see all the things. Thanks, I need to rush to the meeting again.
no problem, sir. Thank you, sir.
Okay, thanks, bye.